Hello students, welcome to MSN Digit Maths. In this video, we are going to see the part 2 of module 3 in unit 1 of sequences and series 7BMA2C2. Here, we are going to cover the topic the algebra of limits. In the previous part, we have studied what is a sequence, what is meant by monotonic sequence, what is meant by bounded sequence, and we have seen convergence, divergence and oscillation of a sequence. Here we are going to see the algebra of limits. Now we are going to see the theorem. If sequence AN converges to A and sequence BN converges to B, then the sum of the sequence AN and BN will converge to the value A plus B. In order to prove the convergence, by the definition, we know that we need a small value epsilon which is greater than 0. Depending upon the values taken by the sequence, this epsilon value may be 0.00001 or 1 or 10 or 100, etc. Right? In order to prove this sequence converges to A plus B, we have to prove that absolute value of an plus bn minus a plus b is less than epsilon, isn't it? To prove that, we are going to use the hypothesis sequence an converges to a and sequence bn converges to b. As sequence an converges to a, by the definition of convergence, there exists a natural number n1 such that absolute value of an minus a is less than epsilon. But we are taking it as epsilon by 2. Let it be, I'll explain that later on, right? So absolute value of an minus a is less than epsilon by 2. This is true for all values of n that is more than n1. Similarly, as sequence bn converges to b, there exists another natural number n2 such that absolute value of bn minus b is less than epsilon by 2. This is true for all n values which is more than n2. Suppose I take the maximum of n1 and n2, that value will be common value that is satisfying the result 2 and the result 3. So I am going to choose such values m, which is the maximum of n1 and n2. Now I take absolute value of an plus bn minus a minus b. This is less than half into epsilon plus half into epsilon. That is less than epsilon. This happened by this factor. What is that factor? Now girls, we know that absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. This is the property of inequality. So by this property, we have absolute value of an plus bn minus a minus b as absolute value of an minus a plus bn minus b. By this method, we take it as two inequalities. Therefore, that is less than or equal to absolute value of an minus a and bn minus b. By 2, we have absolute value of an minus a is less than epsilon by 2. By 3, we have absolute value of bn minus b is less than epsilon by 2. Therefore, we have this total value is less than epsilon. This is true for all values of n that is more than m. Therefore, from this, we proved that absolute sequence an plus bn converges to a plus b. So, we have chosen epsilon is greater than 0. Therefore, epsilon by 2 is also greater than 0. Therefore, when we add, we get this epsilon. In order to get this epsilon here, we have taken this as epsilon by 2 and epsilon by 2. Hence, by the hypothesis, we have proved that sequence an plus bn converges to a plus b. We have to note that instead of plus, if we have minus, the same result will hold on. sequence an minus bn will converge to a minus b. Now we are going to see the next theorem. Sequence an converges to a, k is any real number, then we have to prove that the sequence formed by multiplying k with the sequence an converges to ka. To prove this, let us first assume that because k is a real number, it may take the value 0 also. If it is going to be 0, then kan will be a sequence having the values 0, 0, 0, etc. Therefore, it is converging to 0 into a. Therefore, the result is trivial. So, let us take k is not equal to 0. Then we have absolute value of kan minus ka equal to absolute value of k into an minus a. We also know the property that absolute value of a into b is equal to absolute value of a into absolute value of b. So using this property, we have absolute value of k into an minus a is equal to absolute value of k into absolute value of an minus a. By the hypothesis, as sequence an converges to a, we can find a natural number m such that absolute value of an minus a is less than epsilon. But in the solution part, as we have absolute value of k in the numerator, if we have k in the denominator of this, we can cancel that in order to get epsilon. So I am choosing that epsilon in such a way that absolute value of k is a positive number, epsilon is a positive number. Therefore, epsilon by absolute value of k is also greater than 0. Therefore, I can write absolute value of an minus a is less than epsilon by absolute value of k. This is true for all n greater than or equal to m. Using this result in 1, we get absolute value of kan minus ka is less than epsilon. This is true for all n greater than or equal to m. Therefore, we have sequence kan converges to ka. Now let us see the next theorem. The theorem says, if sequence an converges to a and sequence bn converges to b, then sequence an bn converges to ab. Let us see the hypothesis first. Sequence an converges to a. Then by the definition of convergence, given any epsilon greater than 0, absolute value of an minus a less than epsilon. Similarly, sequence bn converges to b, therefore absolute value of bn minus b is less than epsilon for all n greater than or equal to some other integer n2. For the theorem proof, we need absolute value of a and bn minus ab in the relation of absolute value of an minus a and absolute value of bn minus b. For that, I am introducing a and b. I am adding and subtracting a and b. So I'll have absolute value of a and bn minus ab equal to absolute value of a and bn minus a and b plus a and b minus a. In the properties of inequality, we have absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. Therefore, this relation is less than or equal to absolute value of a and bn minus a and b plus absolute value of a and b minus ab. In the first part of the inequation, we have an common, so it is taken outside. Here we have b a common, therefore b is taken outside. Now, absolute value of b is a constant value, whereas absolute value of an is a sequence value. So, we make use of the theorem that any convergent sequence is a bounded sequence. We have there exists a real number k greater than 0 such that absolute value of an is less than or equal to k for all n. We make use of this here in 1. We have absolute value of a and bn minus ab is less than or equal to k into absolute value of bn minus b plus absolute value of b into absolute value of an minus c. We need this to be less than epsilon. We know that absolute value of bn minus b is less than epsilon and an minus a is less than epsilon. So I can put this as epsilon by 2 and epsilon by 2. In the numerator here we have absolute value of b. Therefore I can put this as epsilon divided by 2 into absolute value of b. This I can put as epsilon by 2 into k. So I am using the hypothesis and I write absolute value of an minus a is less than epsilon divided by 2 into absolute value of b. This is true for all n greater than or equal to the chosen natural number n1. Similarly, as sequence bn converges to b, we can find another natural number n2 such that absolute value of bn minus b is less than epsilon by 2 into k. This is true for all n values greater than or equal to n2. As we have two natural numbers n1 and n2, we choose the maximum of that and have it as m. Now we are applying this in 1, 2. We have absolute value of a and bn minus ab is less than k times epsilon by 2k and absolute value of b into epsilon by 2 into absolute value of b. K and k gets cancelled. This part is epsilon by 2. Absolute value of b and absolute value of b gets cancelled. This part is epsilon by 2. Therefore, we have epsilon. This is true for all n greater than or equal to m. Therefore, we conclude that sequence a and bn converges to ab. Now, let us see the next theorem. This theorem statement is sequence an converges to a and an is not equal to 0 for all n. That means a1 is not equal to 0, a2 is not equal to 0, some ai is not equal to 0 and an is not equal to 0. This is true for all values, as well as a is also not equal to 0. Then we have to prove that sequence 1 by an converges to 1 by a. From the hypothesis we have, for a given epsilon greater than 0, absolute value of an minus a will be less than epsilon. We have to prove that absolute value of 1 by an minus 1 by a is less than epsilon. So we take absolute value of 1 by an minus 1 by a. Let us take the LCM. The denominator becomes an into a. The numerator becomes an minus a. So we can write this as 1 divided by absolute value of an into absolute value of a into absolute value of an minus a. For this part, I can find some epsilon. In the denominator, I have absolute value of a. So in the numerator, I must have an absolute value of a also. Because a is not equal to 0 and because a may take a positive value or negative value, we know that absolute value of a should be greater than 0 because absolute value is going to give the positive value of the given number. Now, since sequence an converges to a, there exists n1 belonging to n such that absolute value of an minus a is less than, we have to put epsilon by 2. From the hypothesis, we have a not equal to 0. Therefore, absolute value of a greater than 0. So, instead of epsilon, we can take absolute value of a. Therefore, we are having absolute value of an minus a is less than half into absolute value of a. Below the definition of convergence, we had a note. In that note, we have noted that absolute value of an minus L less than epsilon implies an belongs to the open interval L minus epsilon, L plus epsilon. In the same way we have, as sequence an minus a is less than half absolute value of a, we can say that an belongs to the open interval. We can take this a to the left hand side, L minus epsilon. So I can put it as absolute value of a minus half into absolute value of a, and L plus epsilon, absolute value of a plus half into absolute value of a. So we have absolute value of an is greater than half absolute value of a. Let us mark it as 2. Now we use this relation in 1. We have absolute value of 1 by an minus 1 by a is less than. We had absolute value of an in the denominator. Therefore, this 2 becomes the numerator. Already we had an absolute value of a. Here we have absolute value of a. So it becomes absolute value of a square into an minus a. We know that sequence an converges to a. Therefore, there exists n2 belonging to n such that absolute value of an minus a is, we have to put less than epsilon. But here we are having a 2 in the numerator. Therefore, we have a 2 in the denominator here. We have absolute value of a square in the denominator. So, we are having absolute value of a square in the numerator. So, this is going to be the result. Now we are going to take m is the maximum of n1 comma n2. We apply this to 2. We get, we apply this to 3. We get absolute value of 1 by an minus 1 by a is less than 2 times absolute value of a square divided by absolute value of a square into 2 into epsilon, which is epsilon. Therefore, sequence 1 by an converges to 1 by a. Now let us see an interesting corollary. The corollary says, if sequence an converges to a, sequence bn converges to b where bn is not equal to 0 for all n and b not equal to 0, then sequence an by bn converges to a by b. First, let us take the bn part. Sequence bn is converging to b. Bn is not equal to 0 for all n. B is also not equal to 0. Then by the above theorem we have sequence 1 by Bn converges to the value 1 by B. We have also seen another theorem saying that if sequence An converges to A and sequence Bn converges to B, then sequence An-Bn converges to AB. Using that theorem, we can write this as sequence an by bn as sequence an into 1 by bn, that will converge to a by b. So, we have a note that if limit n tends to infinity of an and limit n tends to infinity of bn do not exist, even then limit n tends to infinity of an plus bn and limit n tends to infinity of an by bn may exist. That is, maybe limit an is not a converging sequence, bn may not be a converging sequence, but an plus bn and an by bn may be converging sequence. For that, let us take the example sequence an as minus 1 power n and sequence bn as minus 1 power n plus 1. This sequence has alternating terms minus 1 comma 1, minus 1 comma 1, minus 1 comma 1, etc. And this sequence have the value 1 comma minus 1, 1 comma minus 1, etc. So as sequence is a sequence an is a sequence of alternating terms, that is one positive value which is minus 1, second value is plus 1, minus 1, plus 1 and so on. It is not convergent. Similarly, limit n tends to bn also do not exist, but when I add an and bn, we have the first term of an is minus 1, first term of bn is plus 1. Therefore, minus 1 plus 1 becomes 0. Similarly, second value becomes 0, third value becomes 0, etc. Therefore, it is a constant sequence converging to 0. When we take a and bn, we have minus 1 into 1, that will become minus 1. The second term will be 1 into minus 1, that will also become minus 1. And this sequence is going to be the sequence minus 1, minus 1, minus 1, etc., which is a constant sequence converging to minus 1. When we take an by bn, we have the first term is going to be minus 1 divided by 1, therefore minus 1. The second term is going to be 1 divided by minus 1, therefore minus 1, and so on. Therefore, this is also converging to minus 1. Now we come to the next theorem, 3.12. This theorem states that if sequence an converges to A, then absolute value of sequence an converges to absolute value of A. So from the hypothesis, we are having absolute value of an minus a is less than epsilon for a chosen epsilon. This is true for all integers chosen. We have to prove that absolute value of an minus absolute value of a is also less than epsilon, right? So from the hypothesis, we have absolute value of an minus a is less than epsilon for all n greater than or equal to m if we choose epsilon is greater than 0. We are having this relation to be proved is going to be absolute value of an minus absolute value of a. Clearly that is less than absolute value of an minus a. So we have from this absolute value of an minus absolute value of a is less than epsilon. Therefore, sequence absolute value of an converges to absolute value of a. The next theorem is, if sequence an converges to a and an greater than or equal to 0 for all n, then a is also greater than or equal to 0. See, note this, we are having an is either greater than 0 or equal to 0. Then we are having a is either greater than 0 or equal to 0, right? So, we have to prove that a is greater than or equal to 0. In contrary, let us assume that a is less than 0. If a is less than 0, then minus a will be greater than 0. Now, we are going to choose epsilon in such a way that epsilon is greater than 0, at the same time it is smaller than minus a. Will it be possible? Yes, it is possible because minus a is a positive value. So, even if a is going to be 1, minus 1, we are having minus a is 1, then we can choose epsilon lying between 0 and 1. Suppose a is less than 0, which may be minus 5. If we choose minus a, that will be plus 5. I can choose epsilon lying between 0 and 5. So, we are choosing epsilon in such a way that lies between 0 and minus a. In this case, we have a plus epsilon is less than 0. So, when we take this a to the left hand side, we will have a plus epsilon that will be less than 0, right? By the hypothesis, we are having as sequence an converges to a, there exists a natural number m such that absolute value of an minus a is less than epsilon for all n greater than or equal to m. By the definition of convergence, this can be written as an belongs to the open interval a minus epsilon comma a plus epsilon for all n greater than or equal to m. That means a minus epsilon is less than an is less than a plus epsilon. But we have taken that a plus epsilon is less than 0. So I can write this is less than epsilon less than 0. So we have an value is less than a plus epsilon, which is less than 0. So we have an is less than 0. This is a contradiction to the hypothesis that an is greater than or equal to 0. This contradiction happens because we assumed that a is less than 0. Therefore, our assumption is wrong. Therefore, a should be greater than or equal to 0. Now, we have an important note that in this theorem, we have taken an is greater than or equal to 0. Instead of that, if you are going to have an is greater than 0 for all n, we cannot say that a is greater than 0. It may be greater than 0. It may not be also. For example, let us consider the sequence 1 by n. We know that this sequence is made up of 1, 1 by 2, 1 by 3, 1 by 4, etc. No value of this sequence is equal to 0. All the values are greater than 0. But we have also seen the example that this sequence converges to 0. So we have 1 by n is greater than 0. It converges to a value which is equal to 0. Therefore, the above theorem is not true when an is greater than 0. So with this, we are completing this module. Thank you.